All right, well, why don't we start with an example where we just left off with that corollary. So basically what this is saying, okay, so using the factor and root theorem, for example 1, use synthetic division to evaluate a function at the given value of x. Well, we learned, back in Unit 1 or even in Algebra 1, that if I want to find f of 1, this simply means that we plug 1 into the equation where we see x's. And so I did 1 because it was simple. Once you see this process and you see the power of this process, you'll understand why it's very valuable on something like an AP test where you're not given a calculator sometimes to evaluate things. So this example here is perfectly easy to just do the normal way. 1 to the third power would be 1, so 1 times 4 would be 4. 1 squared is 1, so this would be minus 3. 5 times 1 would be 5. And then the minus 2 constant stays there. So then we would just combine like terms, and we'd get 4 minus 3, which would be 1. 1 plus 5 would be 6, and 6 minus 2 would be 4. So f of 1 evidently is equal to 4. So using polynomials, using the factor root theorem, I know that this means that x is equal to 1. That's what this is saying. That is what we did in this other problem. We put x equals 1 in. So I'm going to put that outside of a synthetic division box. I'm going to put my coefficients right here, as we've learned. And then I'm going to do synthetic division. 4 plus nothing is 4. 1 times 4 is 4. Negative 3 plus 4 is 1. 1 times 1 is 1. 5 plus 1 is 6. 6 times 1 is 6. Negative 2 plus 6 is 4. So the remainder theorem says, hey, that number, actually it's the corollary to the remainder theorem, says that this number is exactly the same as this number. So the result is that f of 1, remember we got 1 from here, will produce an output value of 4. Now you might say, big whoop to doodahs, you just plugged in 1. This would work even if it was negative 37. It would still work. And negative 37 would be basically crazy to put here, but here it would not be so bad. So that's the benefit of knowing that corollary. So what else does the factor and root theorem do for us? Well, in problem number 2 here, we have a problem that doesn't factor. And so actually it might factor. It is a quadratic. In fact, it would. And so this first example, I'm going to show you that you can actually use the factor and root theorem to factor a quadratic that previously we may have had to use the box method or grouping method. So here's how it works, same way. We're going to take 4, right? It says x equals 4 right here. We're going to put it on the outside of the synthetic division box. We're going to put a 2 here, a minus 11, and a 12. Just remember that, this is where the square goes, this is where the x goes, and this is where the constant goes. And if this is a 0, remember the factor and root theorem says if this is a 0, then I have factored the problem and the answer will be in the division. So let's take a look at what this looks like. 2 plus nothing is 2. 4 times 2 is 8. Negative 11 plus 8 is negative 3. 4 times negative 3 is negative 12. And so here I get 0, which means that this problem has been factored. As opposed to the original problem that we did where it came out to 4, right? This just means this is the answer. This would be the answer, but basically the connection here is if this is a 0, it had to have come from a factor, right? This is saying this is a 0. And so what factor did it come from? Well, it came from x minus r, or x minus 4. And the other factor is right here, because if this is a square, we learned in synthetic division that this will be an x. And if this is an x, this will be a constant, and the constant produces no remainder. So I would simply get my other factor would be 2x minus 3. And you may recall when we did quadratics that those would be the factors of this. In the quadratic world, we used a box, so we'll just do that again to show you that it does work out to the same thing. So we would start with 2x squared as our our first coefficient. Then we have to lock in 12. Okay, so we look at this and we say, okay, well, how did I make 2x squared? I did a 2x and an x. 12 has a lot of factors. I could use 1 times 12. I could use 2 times 6. I could use 3 times 4. Please keep in mind that 12 is unreasonable, and 2 and 6 can't work because if I put a 2 here, I have a GCF. And if I put a 6 here, I also have a GCF. So the only thing that makes any sense would be to use 3 and 4. Again, I can't put a 4 here because 2 and 4 have a GCF. So I would instead use 3 and 4. I would multiply it through. I would get 8x. Here I would get 3x. And then I would have to come back to the problem and say this problem is an addition problem. This problem is an addition problem that is going to yield negative. So they both need to be negative because a negative times a negative is a positive. So they would both be pulled out to here. And then you can see I got the same factors as I did by using synthetic division. So the question is, where did I get this from? And that will be the next theorem we learn. Like, where did I pull that number from? We will learn that in the next theorem. All right, so staying on this idea of what is the purpose of the factor and root theorem, let's take a look at how to factor this problem here using division as well. Now, you may say, how come you're not talking about the fundamental theorem of algebra? Because we're not currently solving. Right now, we're just factoring. Remember, solving will come later when we set things equal to 0 and try to find their roots. Right now, I'm just giving you some roots. By the way, that's a root. So what do I do with it? Well, you wouldn't try to factor this way. You would probably try to factor this since there are 4 terms. We learned in our last lessons that we would try to use grouping, right? But it doesn't group. You can take out a 2 here, and here you can take out an x squared, but I'm not going to get the same thing in these parentheses. So we're going to move to the factor by division way. But again, where in the world did I get this number from? We will explore that in the next and last theorem for polynomials. So we're just going to assume, okay, thanks for the 2. So I'm going to put a 2 here. And then I'm going to do my inverted synthetic division box, put a 1 here, a -7, a 14, and a -8. Please be aware if anything were missing, like if there were no x squared, I would still put a 0 there, just like we learned earlier. But here, that's why I like to label this up here. It's a very good habit to be in, because if you label this going in descending order, then you will always catch to see if you're missing something. So 1 plus nothing is 1. 2 times 1 is 2. -7 plus 2 is -5. 2 times -5 is -10. 14 minus 10 is 4. 2 times 4 is 8. And lo and behold, we get a 0. We kind of knew that because it told us we could use it here. And so this right here, the purpose of this is to tell you that you have a 0. Right? That's what that actually means. And so what that means is that this will yield the factor of x minus 2. And then this is a square, so this will be, this is a cube, so this will be a square. This is a square, so it'll be an x. This is an x, so this will be a constant. So that'll yield this quadratic. And this is why the quadratic chapter is just so incredibly important. So now we're just going to factor this using the same methods we learned. Now, you might say, why do I have to factor it again? Because you have to keep factoring no matter what. And one of the things that the root and factor theorem says is that there are 3 zeros, and that means there are likely 3 factors. Currently, I have 2. So to factor this, I just start right here. I go forward, right? Notice there's no coefficient, so I can use the easy factoring technique. I have 1 times 4, and I have 2 times 2. And I need to add these together to get 5, so clearly it's 1 and 4. And so I'm going to have x minus 2. And then for this one, I'm going to put my 2 factors here. I'm going to put my 1 here and my 4 here. I'm going to put my x's here. And then to get a -5, I need 2 negatives to make a +4. And this produces the 3 factors that we're likely to get from having a cube. Again, this number means that this is likely. It doesn't mean it's possible. Remember, the fundamental theorem of algebra says there's this many or less if you include imaginaries, and imaginaries can't be factored. All right, so we're going to look at one more theorem and then repeat this process once we figure out how we got this thing. And that's the next theorem we're going to talk about.